All right, in this video, I'm going to be demonstrating a little bit of facts and information about Pascal's triangle. Now, Pascal's triangle was invented a long time ago by a mathematician named Blaise Pascal. And the way you actually create the triangle here, I'm just going to use my pen. So this is it right here. So essentially, what you do is you start off with a 1, and a 1 like that. And then every row after it, all you do is put a 1, and then you add these together. So here and here, that adds to 2, and another 1. Next one, you write a 1. These add together to give 3. These add together to give 3. An additional 1. So even without memorizing this table, you should be able to actually generate it fairly quickly. This becomes 1, 4, 6, 4, and then the end is a 1. So this is a pattern inside of here. Now this pattern is used for a lot of things. You can use it when you're expanding binomials. You can use it for all kinds of different things. So there's a lot of mathematical properties. And we're not going to get into too many details about it in this video, but there's a few things that we definitely want to know about it. And so the biggest thing is knowing how to make it. Okay, so let's keep going here. So again, here's the rules for it. You're going to start and end each row with a 1, and every other term in a triangle is equal to the sum of the two terms immediately, should be above it, not about it, above it. And that's called Pascal's method. Now, in terms of a formula, the formula looks kind of like this. Oops, let me just stop it there. So it says if t, n, comma r, and n and r are subscripts, represents the term in the nth row and position r, then tnr is going to equal to tn minus 1, comma r minus 1, plus tn minus 1, comma r. Now, how does that work in terms of our triangle? So if we compare the two to the way I've labeled this one right here, so the first one is T00. That's the first one right here. The next one, we're on row number 1. Okay. The first one is row 1, position 0, and then it's row 1, position 1. So the first number is the row, and the next one is position number. So it always starts at 0. And so this is element number 0, this is element number 1. So in row 2, that's this row right here. So this is row 2, element 0, that's the first one. Row 2, element 1, that's the middle one. And row 2, element 2, and that's right here. Now, if you look at any of these, basically, if you look at, say, for example, the T3, comma 2, that's going to equal to T2, comma 1 plus T2, comma 2. So essentially what's happening here is you're going T2, comma 1 plus T2, comma 2. So if you add those together, you get T3, comma 2. So this one right here plus this one gives me this one right here. Okay, so now if you take a look at the numbers here, so if you look, the first element here, the 3, if I subtract 1, I get 2. If I subtract 2, I get 1. So that actually matches what I have in my formula up here. So if this was T3, comma 2, the first one is you subtract 1 from it, so it becomes 2. And you subtract 1 from the element number, which is r, and you get that. The next one is the first thing is the row number, it's the n. You subtract 1, and you get T2. And the r stays the same. So if you look, that's actually the formula I've got right here. So that's sort of how I'm relating this. I mean, this is sort of mathy, very, variable dependent, but the biggest thing is I want you to understand the relationship between these numbers and how they work out. So let's actually try some questions here. Sorry, I just need to scroll down. It's going a bit slow here. Okay, so the first one we're going to do T8, comma 2 plus T8, comma 3. So that is going to equal actually to T9, comma 3. So what you do is you increase the row by 1, so the 8's become a 9, and then essentially whatever the bigger one is, that's what goes right here. Okay, so if you look at what we did here, again, the row 2 stayed the same, so they increased by 1, and the bigger element is the 2, so that's the one that gets carried down here. Okay, the next one. So if we're on row 19 for both those, the next one would definitely be on row 20. And the element number would be the one on the right, it'd be 16. So T20, comma 16. Now, I've got one more down here to try out. Just going to expand my page a bit here. So this is a bit weird. So if I've got t5, 3 minus t4, 3, let's go and take a look at those up here first. I want to visualize my triangle first. Oops, it's pretty slow scrolling here, sorry. So I'll try and do this in red. So I'm trying to subtract t5, 3, this one here, and I want to subtract t4, 3, which is this guy right here. So I want to subtract these two. So this thing minus this thing. So if we remember, this one plus this one gives t5, 3, right? So if we subtract this thing, essentially your answer should be this one right here. It should be t4, 2. You could rearrange this equation and you can get it that way as well. But the answer you're looking for is, if you're subtracting the one above it, it's going to be the item to the left here. So it's this one right here. Because I know this number is equal to this one plus this one. So if I have t5, 3 and I subtract away 4, 3, that means I have to be left with 4, 2. So that's the answer for that one. So sometimes you have to look at the little chart just to sort of visualize what's happening here. So this would be t4, 2. And again, what you could do if you absolutely had to is rearrange this. You would know that t5, 3 is going to equal to t4, 4, 2 plus t4, 3. And then you could rearrange it if you had to. So you would go t5, 3 minus t4, 3. That would have to be, because this would become over here, you'd have to be left with t4, 2. So that would be your answer right there. So either way, you get the same result. Now, what is the sum in each row of Pascal's triangle? So let's go ahead and quickly draw out a few rows, and we can see there's a pattern here. Okay, so I'm just going ahead, start with a 1, and then just keep adding up all of the different numbers. Oops, that was a mistake. That is supposed to be a 6 right there. I think this is my eraser. Yeah. 6, 4, and then 1. Okay, so I'm going to make a thing that says sum here. So my first row right here, the sum is going to be 1. The next row, I got a 1 and a 1, that's 2. Next one be 1, 2, and a 1, that's going to be 4. Next one is 1 plus 3 plus 3 plus 1. This is 6 in the middle, plus another 2 is going to be 8. And the last one you're going to see is going to be 16. So this is 5, that's 10, plus a 6 gives me 16. So is there a pattern here? These numbers relate to 2 to the exponent. So this number is actually 2 to the 0. This one right here is 2 to the 1. This is 2 squared. It keeps doubling, so we can represent it as exponents. And this is 2 to the 4 right here. So essentially what happens is the sum of the row is going to equal 2 to the exponent n, where n is the row number. Okay, so that's going to be like a little equation for us that we can use in solving Pascal's triangle. So if you had a question that was like, find the sum of row 14, for example, or row 15. Let's do row 15 as an example. The sum would equal 2 to the 15. Now you can use your calculator to solve that, and that's exactly it. Now if you needed to figure out what row, for example, what row has a sum equal to 2048. So there's a bunch of ways you could do this. We know that 2 to the exponent something has to give me this number, right? It's definitely has to give that number. So you could do a guess and check to solve this. You could keep going to the exponent 4, to the exponent 5, to the exponent 6. You could also use logarithms to solve this. But that's how I would do this. I would just keep guessing the number. It's not going to be that high. And we could just try it out. So I actually don't know the number off the top of my head. Oops. Where's my calculator? Let's just try this out. Oops, I got to turn this into scientific. So I would go 2 to the exponent. I'm going to try 7. I really don't know if that's it. Nope, higher than that. 2 to the exponent. Let's try 9. Nope, getting close though. 2 to the exponent 11. That's it. So it's 2 to the exponent 11. So 2 to the 11 equals this. So therefore, it happened on row number 11. That's where that sum is. So that's all I would do in these questions here. Now, we can use the same principle from Pascal's triangle into situations that are not actually Pascal triangle related. So here's an example of one. It says determine how many different paths will spell Pascal math if you start at the top and proceed to the next row by moving diagonally left or right. So I can't go backwards, I can only go downwards, either left or right. So the way we do this is this. So I'm going to start labeling things. So what I usually do is label on top of each letter. So how many ways can I get to this letter A right here? Well, the only way I can get to it is from the P, and it's one pathway. There's one way of getting there. So this letter A over here, again, one pathway. It's only down here, only one way of getting to that A. Now from this A, I can go to the A or to the S. From this A to the A or the S. And again, I start figuring out my pathways. So how many ways can I get to this S? Well, right now, there's only one way. I can get to the A and then to the S. One way there. Same with this outside S right here. I can come to the P to the A, then to the S, one way. But this S in the middle, what I can do is I can actually go from this A down or from this A down. So if I go 1 plus 1, that actually gives me 2 pathways to get to my S. Oops, I went a bit too far. Okay, let's keep going. So these are all going to connect. And the outer one's pretty easy. It's only one way to get to this C, one way to get to this C. This C right here, I have one pathway coming out of the S, and I actually have 2 pathways coming out of this S right here. So 1 plus 2 gives me 3 ways I can get to this C right here. This C right here, I have 2 coming out of the one on the left, and 1 coming out of the one on the right. There are 3 different ways I can get to this C. Let's keep going. So it's very repetitive, the same process over and over and over again, and we'll figure out the answer at the end. So I have one pathway out of the C, 3 out of this C, gives me 4 ways of getting to this A. The middle A, there's 3 out of this letter C, 3 out of this letter C, gives me a total of 6 ways of getting there. And then 3 out of this one, 1 out of this one gives me 4 ways to get to this A. Okay, let's keep going. We get to the L's. So the L, I've got 4 roots out of this A, 6 roots out of here, I get 10. And 6 roots out of this A, 4 roots out of here, I get 10 again. And we keep going. So this M in particular right here, this was a bit of a weird one because really the only way to get to it is from this L. So you're just going to use 10 again right here. So the only way is I have to go directly from the L. It's almost like L plus 0. You can think of like a 0 up here. So 10 plus 0 gives me just 10. Same with this one on the outside here. It's just another 10 again. The inside M though is I have 10 roots from the left M and 10 roots from the right M. Gives me 20 roots in total to get to this M. Then we keep going. Okay, this outer A over here, I've got 10 roots to get to this one, and 10 roots to this outer A. And then the inside one, I've got 10 roots from this M, 20 from here, gives me 30. And then this one will also be 30. Now I'll just quickly continue going here. I've sort of explained the process already, so hopefully it makes sense. This will be 10, 40, 60, 40, and 10 again. And then finally we get to these H's. So this H, I have 10 out of the left and 40 out of the right, so it's 50 ways to get to that one, 100 ways to get to this guy, 100 to this one, and another 50 right here. So now my path can end with this H, or this H, or this H, or this H. So because this is an OR situation, I need to add these. So the total number of routes to get to an H is 50 plus 100 plus 100 plus 50 is going to equal to 300 ways. So 300 different ways of spelling out Pascal math. Okay, next example I've got here. It says, Mason lives 5 blocks east and 4 blocks south of Graham. How many different routes are possible for Mason to take to Graham's house if he only walks north and west? So it's important to note the directions that I'm allowed to go. So Mason is currently 5 blocks east. So 1, 2, 3, 4, 5 blocks to the east and 4 blocks south. 1, 2, 3, 4. So you may have to draw this grid in if you don't have it. Now, how many ways can I get from this M right here up to this G? And I can only go to the upper left direction, north and west. So here's how I solve this question. So I consider the intersections. So I'm starting here. How many ways can I get to this intersection? Only one way. I can go straight up, and that's it right there. Same with this intersection right here. There's only one way I can get to that intersection. Okay, let's keep going. This one right here, there's only one way I can get to it. I have to go here, and then I have to go here. There's one way to get to that one. Same with this one right here. I can go here, and then here, so west-west both ways. Gives me a 1. But this one right here, I can go left and then up. That's one route. Or I can go up and then left. So it's basically I have a 1 coming from one direction and a 1 coming from another direction. 2 different ways of getting to that point. I could do this one next right here. I have 2 routes coming out of this point and 1 route coming out of this point. Gives me a total of 3 different ways of getting to this dot right here. I could do this one next. I have 1 route coming out of the bottom and 2 routes out of this one. Gives me a total of 3. And we just keep filling this out. So there's one way of getting to this dot. There's one way of getting to this dot. The only way is straight up. I'm going to keep going along the outside here. And you just sort of progress your way up to the G. So one way to get to here, one way to get to here, and one way to get to here. The only way to get to any of these is straight along this line. Okay. Now, let's see what else we can fill in. So this dot right here, I've got a 1 coming out of here and a 3 coming out of here. This gives me 4. This dot I could do next. A 1 coming out of here and a 4 coming out of here gives me 5. So 5 different routes to get to this point. And this one, I have 1 route coming out of the bottom and 5 possibilities out of the right. Gives me 6 ways of getting there. Okay, let's come back over here now. This location here, I've got 1 coming out of there and 3 different possibilities coming out of here, which means I have 4 ways of getting to that circle. And this circle right here, I actually have 5. So 1 coming out of here and 4 coming out from the bottom here. Okay, inside of here, I've got 3 possibilities to get here and 3 possibilities to get here. Gives me a total of 6 possibilities for this dot here. This location here, I have 6 coming out of here, 4 coming out of here gives me 10. And then this one here would be 15. So I'm going to start skipping through it here, so hopefully you understand the pattern, what I'm doing. But I'm just adding as I go here. This one here, 4 plus a 6, that gives me a 10. 5 plus a 10 gives me 15. And a 6 plus a 15 gives me 21, right there. This dot right here, I have a 10 plus a 10 gives me 20 routes to this one. And from here, I would have 20 plus 15 is 35 routes to that dot. This dot right here, I've got 20 plus 15, that gives me 35 to this location. And then from here, I would have 35 plus 21. That gives me 56 ways of getting to this dot. This dot right here, 35 plus the 35 gives me 70. And then finally, the very last final location, I have 70 routes out of here and 56 routes out of here. That gives me 126 different routes. So that's how you fill this out. You sort of progress your way from the M to the G. You got to watch the wording of these questions, make sure they're worded properly. And once you draw your grid, you should be able to solve this. So therefore, there are 126 ways of getting to grams. Okay. Trying to speed this up here so it's a little bit faster. Okay, the last one. I'm taking a road trip to Winnipeg. Below is a diagram that represents the different routes you could take. How many different routes are there from Thunder Bay to Winnipeg? You really got to watch the arrowheads on this. You can't go backwards and things like that, so you got to watch the directions you're allowed to go. This is actually a very easy question. So from Thunder Bay to Atikokan, really, there's only one way of getting there. I have to go straight along this line. Okay, the next one, let's do is Fort Frances. The only way I can get to Fort Frances is I have to come out of Atikokan only one way of getting there. And we can actually do Dryden next. So Dryden, I can have one route out of Thunder Bay, one route out of Atacocan, and one route out of Fort Francis. 3 different ways of getting to Dryden, according to this diagram. Let's do Rainy River next. So Rainy River, the only way I can get there is straight along this pathway. There's only one way in, and that's from Fort Francis. So there's one way to get to Rainy River. Kenora, though, let's look at Kenora now. So I have one pathway out of Rainy River, that's one. I have one pathway out of Fort Francis, there's another one. And then 3 out of Dryden. So Kenora actually has 5 different ways of getting into it. One from Rainy River, one from Fort Francis, and 3 pathways from Dryden. Okay, Sprague is next down here. There is only one way of getting there. That's straight out of Rainy River. Steinbeck, one way, straight out of Sprague here. And then finally, Winnipeg, I have one mechanism out of here, or one pathway out of here, and 5 out of Kenora. Gives me a total of 6 different things coming in. So 5 plus 1 gives me the 6. So the answer is therefore, there's 6 routes possible. Ooh, routes possible. Oh boy, I cannot spell today. 6 routes possible. Yeah, so this is some of the applications of the Pascal's triangle concept. It's not Pascal's triangle, but it's a similar sort of addition mechanism. And hopefully this lesson makes some sense to you. This is going to be the homework today out of the textbook. And hopefully everything makes sense and you don't have any questions. And yeah, that's a little lesson on Pascal's triangle and how it could be used to solve mapping problems and probability problems.